Welcome to the last video in the relativity series. The final topic of this one is relativistic momentum. So the relativistic momentum of a moving object is given by the Lorentz factor times the mass of the object in the frame of reference in which it's stationary, and then times by the velocity of the object. So this equation here. In stage 2 physics, you'll be expected to be able to solve problems using this equation, and you'll also need to be able to explain why moving masses at relativistic speeds are unable to reach the speed of light. And just a reminder that relativistic speeds refer to speeds that are greater than or equal to 3/10 of the speed of light. So previously in relativity, we were looking at Galilean transformations. These are applicable to classical physics. They state that u, so the velocity as measured in reference frame A, is equal to the velocity measured in reference frame B, or u prime, plus v, which is the relative velocity between the two reference frames. If you rearrange this, you'll get this equation here, and that gives you the velocity as measured in reference frame B. And then same again, rearranging, you'll be able to get this equation here, which gives you the relative velocity between your two reference frames. These, however, require modification to account for the impacts of special relativity. And when these are modified, they're called Lorentz transformations or relativistic velocity transformations. So for particles travelling at relativistic speeds, the velocity in reference frame A is equal to the velocity in reference frame B, u prime, plus the relative velocity, and then that's divided by 1 plus the velocity in reference frame B times the relative velocity divided by the square of the speed of light. Similarly, for the velocity in reference frame B, this is equal to the velocity in reference frame A minus the relative velocity between the two reference frames, and then that number divided by 1 minus the velocity in reference frame A times the relative velocity divided by the square of the speed of light. These alterations have implications for velocity-dependent quantities, so for example, momentum. Special relativity states that the law of conservation of momentum, and indeed the law of physics, are the same or valid in all inertial reference frames. But for colliding particles moving at relativistic speeds, analysis using the momentum equals mass times velocity equation in stationary and moving reference frames indicates that momentum is not conserved, so this needs to be adjusted. So the relativistic momentum of a particle is given by this lovely whopping big equation here. It's not actually that big, it just looks big with the fraction and square root sign of the Lorentz factor. This illustrates that when velocity is much less than the speed of light, so it's at a classical or tangible speed that's not supermassive, the relativistic momentum will be roughly equal to the classic momentum, and that's because this here, which is the Lorentz factor, will be equal pretty much to 1. So if v here is a pretty small fraction of c here, then this little fraction here will be equal to 0, therefore this big fraction will be equal to 1. Hence it'll be 1 times mv, and that'll just be equal to pretty much p equals mv. However, when v approaches c, the Lorentz factor becomes more close to infinity because this fraction here is becoming closer and closer to 1, and we're getting closer and closer to 1 minus 1, and therefore closer and closer to the Lorentz factor becoming infinity, hence the relativistic velocity is infinity times mv, and so it becomes closer and closer to infinity. The Lorentz factor provides a measure of how much, or the amount, that the relativistic momentum differs from the classical momentum. So as I was kind of touching on just before, when v is much less than c, the Lorentz factor is pretty much equal to 1, so it's kind of just like classical physics, or classical momentum, whereas when v is approaching c, the Lorentz factor is approaching infinity, and hence the relativistic velocity is approaching infinity. So these graphs just reiterate what I was saying on the previous slide. So when the velocity is like a small fraction of the speed of light, or a very small fraction of the speed of light, the relativistic momentum is pretty much equal to the classical momentum, and that's indicated around here where the two lines are sitting on top of each other. We've got the special relativity graph in red, and then the Newtonian or classical graph in green. I'll just mention that this speed here is the fraction of c, so it's what v is a fraction of c. So at 1, that's when v is equal to c. And as v approaches c, the relativistic momentum becomes, or it approaches infinity. So that's why it begins becoming more or less a vertical line as that v approaches c, or as the ratio is equal to 1. And this graph on the right provides an indication of the Lorentz factor plotted against the fraction of v on c, so the ratio of v to c. As v is less than 3/10 of the speed of light, the Lorentz factor is equal to 1, or pretty much equal to 1. It's only when v starts becoming greater than 3/10 of the speed of light that we start seeing an increase in the Lorentz factor here, and that sharply increases the closer and closer v gets to the speed of light. So we can do an example question now. So for example, a proton with a mass of 1.67 times 10 to the negative 27 kilos. You'll have this figure on your cheat sheet or formula sheet. This proton is accelerated to 0.9999 of the speed of light. What is the relativistic momentum of this proton? So to find this, you just use your momentum equals the Lorentz factor times the mass of the proton in the reference frame that it's stationary in. So in the moving reference frame, but in its own reference frame, it's stationary. So the moving reference frame is moving relative to a stationary observer. And then times the velocity, or the relative velocity. And this is obviously equal to the Lorentz factor, which is 1 divided by the square root of 1 minus velocity squared over speed of light squared, and then times by that mass in its own reference frame, so the reference frame that it's stationary in, times by the relative velocity between the two reference frames, so between the stationary reference frame and the proton's reference frame. Subbing in our values, this will be 1 over 1 minus, and then 0.9999c squared over c squared. And then the mass is 1.67 times 10 to the negative 27. And the velocity between the two reference frames is going to be 0.9999c. Oh, just made it in. by the skin of my teeth there, because the observer is stationary, so whatever the velocity of the proton is going to be the relative velocity as well. And then if you were to type all of this into your calculator, you would end up with 3.54 times 10 to the negative 17 kilogram meters per second. So that's how you'd find the relativistic momentum of this proton. So moving on to our second content skill for this last part of relativity, the Lorentz factor and the relativistic momentum approaching infinity impacts the relationship between momentum and force. So Newton's second law of motion states that force is equal to the change in momentum divided by the change in time, or in other words, the rate of change of momentum. And this is still valid as long as the relativistic momentum is used. Because with relativistic momentum, it's no longer directly proportional to v, or to velocity, the rate of change of momentum is therefore no longer directly proportional to acceleration. Therefore, a constant force doesn't equal or doesn't result in a constant acceleration when particles move at relativistic speeds. So that's different to our classical physics or Newtonian physics understanding. Those rules tend to break down as particles or as bodies approach the speed of light, theoretically. So instead, our equation for force is this bad boy here. And this applies if the force and velocity, so the constant force and velocity, have the same direction. This is equal to, so force is equal to the Lorentz factor to the power of 3 times my mass by acceleration. So to elaborate on this rule a little bit more, if we've got this rule here, then we can also say that acceleration is equal to force divided by the Lorentz factor to the power 3 times by mass. Therefore, acceleration is inversely proportional to the Lorentz factor cubed. We know that the Lorentz factor is equal to 1 on the square root of 1 minus v squared over, 1 minus v squared, the relativistic velocity squared, divided by c squared. Therefore, as the speed increases, so the speed of a particle as v increases, or the relativistic velocity increases, then the Lorentz factor increases as well. Because we've got v here getting closer and closer to the speed of light, and then this whole fraction therefore becoming 1, and then this denominator therefore becoming 0, which means that this whole fraction would be approaching infinity, because as the bottom of a fraction gets smaller and smaller, the overall number becomes bigger and bigger. So if A is inversely proportional to a Lorentz factor that's becoming bigger and bigger, then this overall fraction here will be becoming smaller and smaller, because the denominator here will be getting larger and larger, even more so because the Lorentz factor is being cubed on this denominator. So as velocity increases, then acceleration will decrease. So as a particle's speed increases, its acceleration decreases. Another way of saying this is that the ability of a particle to be accelerated, so its inertia, decreases as the particle speed increases. So as v, or the velocity of the particle, approaches c, and incidentally, as momentum approaches infinity, a, or the acceleration, approaches zero. No matter how large our force is here. This is why the speed of light, c, is sometimes referred to as the cosmic speed limit, because as a reaches zero, so as acceleration reaches zero, when velocity becomes equal to the speed of light, the speed can't be accelerated beyond c because acceleration has already reached zero. Another way of stating this is that force can't accelerate a particle beyond the speed of light because momentum, as I touched on just before, has already become infinitely large as speed reaches c. So as the fraction or the ratio of the relative velocity to the speed of light is equal to 1. The force required for each additional increment of velocity becomes larger and larger until no amount of force can increase the particle's velocity any further. And this point, where no amount of force can increase the particle's velocity any further, occurs when the relative velocity, v, becomes equal to c, the speed of light. So hopefully that explains why masses moving at relativistic speeds are unable to reach the speed of light.